This telescope mounting invention grew from a high school avocation of astronomy, and more specifically, from telescope making. As a hobby, it was also influential in my becoming an industrial designer, followed by working at General Motors Styling, and then the GM Defense Research Laboratories in Santa Barbara, working on gas turbine Motorama concept cars, and then lunar roving vehicles. I was exposed to skilled craftsmen and learned prototyping techniques that would influence my telescope and inventions within that continuing avocation, including this waterborne telescope mounting. It was nationally shown at the Mecca of amateur astronomy in Stellafane, a convention held in Springfield, Vermont, almost 50 years ago in 1967. The mounting's most outstanding property is its near instantaneous thin film damping. This is because any vibration or oscillation of the sphere will demand rapid acceleration and deceleration back and forth of the fluid mass in the base. Masses just don't like to do this. As the depth of the immersion encompasses a relatively large footprint to work against, this offers broad-based stability. In its earliest forms, a light sponge foam rubber resistance was added around the perimeter to hold the sphere stationary while observing. Drive systems were also explored and will be discussed. Early attempts to drive the telescope were boilerplate and only for visual tracking. A suction cup secured to a drive shaft was surprisingly easy to make work. It was followed by a meridian belt attachment to induce potential elevation control. While there was satisfaction that they worked, it was also observed that soft attachments to the sphere at one point created a fulcrum reference, and any variations in fluid level could introduce upsetting problems. In the decade following, I left GM and went into aerospace, and in my avocation, I went into a period of developing prototypes. The payload chart maps out several generations of telescopes and designs. The largest and last telescope I built was the 12.5-inch f5 Richesfield type that embodied the best features of all the preceding telescopes. Fiberglass shells laid up in plastic tooling was my medium of choice. This cutaway shows those best practices. A transverse bulkhead couched in a 9-point flotation cell for the primary mirror, accessible from the front through a service port. A cover and annular collar protect the mirror face and edges. In a carrier, it can easily be dropped in place to pivot into its support pocket. A later generation suction cup clock drive was set up that could actively draw a vacuum to lock the sphere to the drive shaft. The ultimate objective was to change from a vacuum suction to a positive fluid flow to force separation, and then vacuum re-engagement for tracking. While duplicating some prior concepts, this slide does show the scope of the activity, transitioning from prototyping to conceptual design for larger telescope concepts. I exited the "what can I do in my garage" methodology. While working for Tessa Design, I submitted a small business innovative research proposal to test some observatory class Spheremount concepts evaluating gyro-stabilized systems. In 1968, I purchased 3 World War II surplus gyros, intending to experiment with gyro stabilization. The key factor was that in order to work, the gyro could be passive. As the stars are not really moving, all that would be needed would be to hold the telescope stationary. I was never able to test that hardware. Continuing investigations into hardware became more theoretical as scales increased to the observatory classes, and as shown above, concerns migrated to service and maintenance, like how do you replace some of these big things when you have a building sitting on top of them? The driver in the above study was that by intermixing fluid bearing systems, you could increase pressures and be able to use smaller bearings. Likewise, using multiple bearings, you'd be able to function without the full set under typical service modes. This slide illustrates the basic assumption of the sphere mount, that under full flotation, you can allow the Earth to rotate under it if it's inertially locked in space by gyros or other, and you will be automatically tracking the stars. In a variation right, it is proposed to introduce a fluid flow from west to east that would have sufficient drag to offset any earth forces trying to turn it. Shown is a method using east and west reservoirs and manifolds to induce a cross flow under the sphere so that a delta pressure head between the reservoirs can be tuned to offset that earth rotation. This, of course, would require development and verification. The rationale is that it should be easier to isolate the sphere from Earth and stop the rotation than it will be to induce motions reacting from a dynamic complex Earth reference through a 30-meter spring to induce tracking vectors. Another asset of the sphere mount is that it separates the functions of a mounting into support and tracking, and they need not use the same hardware for both. Tracking need not require support or damping functions support. As implied earlier, by attaching equatorial or alt-azimuth type hardware to the sphere for tracking introduces a fulcrum point from which tangential disturbances can impart angular or deflection errors into the system. The ideal system will have free flotation and a gyroscopic or inertial reaction wheel system to counter or induce other desired torques to track objects. This, in effect, has already been proven or verified by the Hubble telescope. With the advent of adaptive optics and multi-mirror telescopes, the size of observatories has grown exponentially. The basic elements of sphere-mounted telescopes in this class are shown here, adapted for the 30-meter telescope and the giant Magellan telescopes. These are shown for scale reference only, as these telescopes are committed to their hardware. The sphere mounting is suggested for observatory telescopes of the future, and the likelihood is that they will be gyro-stabilized. A closing audio record is inserted here for background of a gyro test recorded in 1960.
And of course I have the gyro assembly all set together. Tell you what, I think I'm going to stop this tape here for an instant and start it up and record the sound of the startup. Okay, I don't know how this thing's going to work, but plug it in. This is the sound of telescopes in the future. These are 3 war surplus gyros, each weighing about 13 pounds. 3 of them makes up an assembly of about 40 pounds, which I have to float. Still revving up. It'll keep revving now for several more minutes. Still winding up. I'm going to touch the microphone to the side of the cylinder. I don't know if this will make a noise or not. Probably will. Okay, that's it. I'm going to shut down now and play us back. That's shut off and slowing down now.